Okay, so we're all here. All right, good. So, so what I was saying is, yeah, so can you just enable my screen sharing, Bappa?
10 minutes, I'll make you host.
Okay, okay. Okay. Thank you. Okay. All right. So what I was saying is that singularities of the vector field are fixed points of the flow. Is this clear? So note that, see, vector field X gives flow phi t p maps to gamma p of t. But you can go backwards. A flow phi t, so here t and r, a flow phi t, you can recover the vector field from the flow, gives you vector field. How do you get xp? So xp is equal to ddt at t equal to 0 of gamma pt, right? By definition, gamma p is an integral curve. So xp is nothing but ddt at t equal to 0 of phi t of p. Is this clear? So by differentiating the flow at time 0, you get back the vector field. All right? Is this okay? Yes, are you there?
Yes, it's fine.
Yes.
Okay. All right. Okay. Good. So now I want to move on to what's called the Lie bracket of vector fields. Okay. So any vector field X, algebraically, what does it do? So algebraically, it defines what's called a derivation of the ring of smooth functions C infinity n. So it defines a map X from C infinity n to C infinity m. F maps to XF, where XF is the function whose value at P is the following. So XF at P is basically XP acting on F. So remember, XP is a tangent vector at P. So it's a derivation at P. So it acts on a function defined near P. So it can act on F and give you a real number, right? So XP at F is defined to be the value of the function XF at P. Is this clear? So this gives you a map from C infinity M to C infinity M. And it's clear that because each XP is a linear map from the tangent space to R, this map is linear in F. And also because XP is a derivation at P, this map satisfies the Leibniz rule for this ring C infinity M. In other words, X of F times G is XF into G plus F into XG. Right? Is this clear?
Yes, sir.
Okay. So algebraically, a vector field defines for you what's called a derivation of the algebra C infinity M. That means a linear map from C infinity M to C infinity M, which satisfies the Leibniz rule for C infinity M. Okay. X of Fg is XF into G plus F into XG. Okay. Now, what I want to say is actually This gives us all derivations of C infinity M. In other words, there is a one-to-one correspondence between smooth vector fields on M and algebraically derivations of the algebra C infinity M. Okay, so how do we go backwards? Well, suppose I have a derivation L from C infinity M to C infinity M. Okay, so that means it's a linear map which satisfies the Leibniz rule. Then I can define a vector field X on M as follows. So I have to define for each point P, I have to define a tangent vector at P, right? So XP is going to be a linear map from the ring of germs C infinity MP to R. What does it do? Well, I take a germ of smooth function F. Then what I do is I can extend that by multiplying by a suitable bump function, which is 1 in a neighborhood of P and say 0 outside a neighborhood of P. I multiply by a bump function on M, a smooth bump function. Then I can extend it to a globally defined function, a smooth function on all of M. Now my derivation L can act on that smooth function defined on all of M. So let me call that F tilde. So F tilde is a smooth extension of the germ to all of M. Is this clear? So F tilde is equal to F in a neighborhood of P. I don't care what happens outside a neighborhood of P. And then I let L act on F tilde, and then I evaluate it at P. So that gives me a real number. So I get a map from C infinity MP to R. Okay. Now I have to check that this is well defined, independent of the choice of extension, right? Is that clear? I need to check this is well defined, right?
Yeah.
Yes?
Yes.
Right, I have to check this is well defined. Okay. So suppose I have two extensions, F tilde and G tilde. Both are equal to F in a neighborhood U of P. So then what I do is I choose phi, a smooth function with compact support contained in U, such that phi of P is equal to 1. Okay. Then if I look at the function F tilde minus G tilde into phi, this is identically 0 everywhere on the manifold. Why? Because if I am inside the neighborhood U, then F tilde is equal to G tilde is equal to F. So F tilde minus G tilde is 0. And if I am outside the neighborhood U, then the function phi is 0 because its support is contained in U. Right? So this function is identically 0. Okay? Yes?
Yes, yes.
Okay, now L, my derivation L from C infinity M to C infinity M, this is a linear map, so it sends the 0 function to the 0 function. So therefore 0 will be equal to L of F tilde minus G tilde into phi evaluated at P. Okay, now I use the Leibniz rule. I know that L is a derivation. So this will be L of F tilde minus G tilde at P into phi of P plus F tilde minus G tilde at P into L phi of P. Okay. So now the second term vanishes because F tilde minus G tilde at P is 0. So this second term goes away. So what remains? This phi of P is 1. I've chosen phi so that phi of P is 1. So then this becomes LF tilde P minus LG tilde P. So this difference is equal to 0. So therefore LF tilde P is equal to LG tilde P. Right? So this means that this LF tilde is well defined, independent of the choice of extension. Is this clear?
Yes.
So therefore, and then once you can see that it's well defined, then it's easy to see that this is linear and satisfies the Leibniz rule at P. Is that clear? Because L is linear and satisfies the Leibniz rule at P. Okay. Yes?
Yes.
All right. Okay, so therefore this defines a tangent vector. So therefore I get at each point P, my derivation L, which was a global object, defines at each point P a tangent vector XP. So therefore I get a vector field XP, all right? A well-defined vector field. And now I want to say that this vector field that I've got is smooth. Okay, this is a smooth vector field. Why is that? Because if I take a chart, phi, say it's x1 to xn near a point P naught, then what I do is I extend my xi's to, these are locally defined functions near P naught. I extend them to global functions, right? Again, by multiplying by a bump function, which is 1 in a neighborhood of P naught. I extend them to global functions, smooth functions on M, xi tilde. Then if I look in my chart, what is xp? So xp is a linear combination of the del del xi's. And what are the coefficients of the del del xi's? So remember, if I had any tangent vector, then the coefficients of del del xi was L of xi, right? We saw that last time. The coefficient of del del xi was L applied to xi. So this will be xp applied to xi, right? And xp applied to xi, by definition, this will be L of xi tilde at P, right? Yes?
Yes.
Yes. Yes.
Okay, but now L is a map from C infinity M to C infinity M. So therefore, L of xi tilde is a smooth function. Therefore, my coefficients of my vector field are smooth, right? Therefore, my vector field X is a smooth vector field. Is it clear? Okay, so to sum it up, we have geometrically, we have chi-m. This is smooth vector fields on M. And this corresponds, there's a one-to-one correspondence with a purely algebraic object, derivations der of C infinity M. Okay, so this is derivations of the R algebra C infinity M. Okay, is this all right? Yes? Hello, are you there?
Yes, sir. Understood.
Understood. Okay. So we have this one-to-one correspondence. Now, on the right-hand side, I have an extra operation, which is, so derivations are maps from C infinity M to C infinity M, right? So if I have two such derivations, x, y, from C infinity M to C infinity M, then I can compose them as maps, right? So I can look at x composed y, which I'll write as just xy, and I have also yx. These will be maps from C infinity M to C infinity M. Yes? Okay. Now, these are x and y are first order, what I was calling first order differential operators. So when I compose these two first order differential operators, xy and yx, these will be what are called second order differential operators. So for example, x could be in a local chart del del xi. If I do del del xi twice, compose del del xi with del del xi, then I get the second order operator del squared del xi squared, right? That's a second order differential operator. Or if I compose del del xi with del del xj, then what will I get? I'll get del squared del xi del xj. That's a second order differential operator. Okay? But something very nice happens if I take the bracket of x and y. So this is defined to be xy minus yx from C infinity m to C infinity n. Then what happens is actually when you take the difference of these two second order differential operators, the second order terms cancel out and you're left with first order terms, and this actually becomes a derivation. So this you can check algebraically. It's just a simple calculation, which I won't do. I'll leave it as an exercise for you. This is a derivation of C infinity n. Okay, so this is a first order differential operator. Okay, so check. So as an exercise, check this. All right, it's an easy exercise, just calculation. Okay.
Okay.
All right. So therefore, this corresponds to a vector field. So a vector field xy. Okay, so if I have xy belong to chi-m, then I get another vector field bracket xy belonging to chi-m, which is called the Lie bracket of x and y. Okay. All right. So,
Sir, via checking that if this is a derivation, we can then, by the previous identification, we get that this is a smooth vector field on M. So
yes.
first order differential operator. But you said that the second order the terms cancel out. I didn't understand how we see that.
That's by equality of mixed partial derivatives. It boils down to that. Del squared del xi del xj is equal to del squared del xj del xi.
Oh, as in a Euclidean situation.
If you do it in coordinates, but I'm saying you don't need to do the coordinate computation. You just show that this satisfies the Leibniz rule. Basically, you look at xy minus yx applied to, so show xy minus yx applied to f times g is equal to xy minus yx applied to f into g plus xy minus yx of g into f. Just show this. This is a purely algebraic computation. You just have to use the fact that x and y are derivations. So this is purely algebraic. This works for any ring. You take any ring and you take a derivation of the ring. That means a map from the ring to the ring. a commutative ring, let's say, which satisfies Leibniz rule, then for any two derivations of the ring R, the bracket of the two derivations, xy minus yx, will also be a derivation. This is pure algebra, pure algebra. Is that clear, Utsav?
Yes, sir.
So just check this. This, you just have to use the fact that, so if R is a commutative ring, then you have an operation bracket from der R cross der R to der R. Okay.
Yes, sir.
Understood? So there's no manifold, no coordinates, nothing. It's just pure algebra, just algebra. Is it clear now?
Yes, sir.
You just have to check the derivation property, right? Linearity is clear because composition of linear maps and sum and difference of linear maps is linear. So the linearity is clear. You just have to check the derivation, the Leibniz rule, right? You just have to check the Leibniz rule. That part is pure algebra. What I'm saying is, if you try and do it in coordinates, then you will see what happens is the second order terms cancel because of equality of mixed partial derivatives. Okay, if you try and write out a coordinate expression, then what you'll see is that the second order terms cancel because of equality of mixed partial derivatives. Is it okay now?
Yes, sir. Yes.
Okay. So, we have this bracket operation. So the bracket, Lie bracket, is one. So it's easy to see this is bilinear. Right?
Bilinear with respect to the
What did I write? Yeah, it's bilinear. Maybe it's here. Let me see. Okay, I haven't written anything about it. I wonder where I wrote. Anyway, so it's bilinear with respect to addition of vector fields, right? Addition and scalar multiplication of vector fields is bilinear, skew symmetric, so or alternating. So that's immediate from the definition. Bracket of xy is minus bracket of yx. This is clear, right? You just look at what the derivation is, right? Yeah, this is alternating, skew symmetric. Is that clear?
Yes, yes.
And it satisfies, again, from the definition you can check, it satisfies what's called the Jacobi identity. So that's a sort of triple symmetry. So X bracket, if you write the brackets of three vector fields in cyclic order and add them up, X bracket YZ plus y bracket zx plus z bracket xy is equal to 0. Okay. So, a vector space with a bilinear operation which satisfies these properties is called a Lie algebra. So, bracket. So, chi m with the operation bracket from chi m cross chi m to chi m this pair is a Lie algebra. Okay. So you may have heard of Lie algebras and Lie groups. So Lie algebras are in a sense infinitesimal forms of Lie groups, where Lie groups are groups which are also manifolds, where the group addition, multiplication and inversion are smooth maps of the manifold. So for example, the matrix groups GLNR, SLNR, ONR, the orthogonal group, the special orthogonal group, and so on. All of these are Lie groups. But those are finite dimensional Lie groups. Associated to them are finite dimensional Lie algebras. So for example, associated to the orthogonal group, let's say a simple example, associated to SLNR, there is an associated Lie algebra, which is the Lie algebra of matrices of trace 0. Okay, so what happens is actually you know this probably for a topological group, any neighborhood of the identity, if the group is connected, then any neighborhood of the identity generates the whole group, right? Have you seen this?
Yes, sir.
Yes, sir. Yes.
Yes, sir.
The proof is very easy. You just look at the group generated by it and show that it's open and closed, right? Show
Yes.
that it's open and closed. So for a connected topological group, you take a tiny neighborhood of the identity, it's going to generate the whole group. So that means in some sense, all information about the group is contained inside any neighborhood of the identity. Okay, now if you're doing calculus and your group is a Lie group, so it has a smooth structure, then you can look, instead of looking at smaller and smaller neighborhoods of the identity, what you actually want to do is look at the tangent space to the identity. So that's a finite dimensional vector space. You look at the tangent space to the identity, and it turns out that this has the structure of a Lie algebra. It's a vector space, right? This has the structure of a Lie algebra. And how do you get a Lie algebra structure? Well, you take any tangent vector at the identity. Now, by left translations, you can you can transport this tangent vector to tangent vectors at all points of the group. So you get what's called a left invariant vector field on the group, all right? And now if I take two tangent vectors at the identity, then they will give me two left invariant vector fields on the group. And then I can take the Lie bracket of those two vector fields as a Lie bracket of vector fields on a manifold. So I get a new vector field, and it turns out that the Lie bracket of left invariant vector fields is also left invariant. Okay, and then I restrict that to the identity. I look at its value at the identity. So that gives me a new tangent vector at the identity. That is the Lie bracket of the two tangent vectors at the identity. Okay. So any Lie group, there's an associated Lie algebra, which is just the tangent space to the identity. Okay, so if I look at SLN-R, then SLN-R means what? Determinant 1 matrices, right? So what is the tangent space to the identity? I look at the derivative of the determinant map at the identity. I think of the determinant as a smooth map from MNR to R, from the vector space MNR to the real numbers. And so the special linear group is the inverse image of 1, right? Det inverse of 1. So the tangent space to the identity will be the kernel of the derivative of the determinant, right? And what is the derivative of the determinant at the identity? It is the trace, right? It is the trace. So therefore the Lie algebra, the tangent space to the special linear group will be the matrices with trace 0. Is this clear? So that's why they will form a Lie algebra. Okay. And the bracket operation for a matrix group, it turns out to be just the usual bracket of matrices. If A and B are two square matrices, their Lie bracket is AB minus BA. That's another square matrix, right? It turns out to be just the usual bracket operation. So you can see that trace 0 matrices are closed under taking brackets, right? Because trace of AB is equal to trace of BA. So therefore trace of AB minus BA will be 0, right? So therefore bracket 0, trace 0 matrices are closed under bracket of matrices. So they form a Lie algebra, all right? Okay, so that was a crash course in Lie algebras and Lie groups, just to give you a little idea. I hope it didn't go too far. Anyway, so
Sir, hello.
yes.
Sir, we have just 8 minutes or more. So should we join again or?
No, I think let me finish. I have 8 minutes. That's enough to do the last proposition I want to do today.
Okay. Okay.
Which is the following. So now we look at these notes. All right, so we have this Lie bracket. And we can also, given two vector fields, we can define a sort of derivative of one vector field with respect to the other, which is called the Lie derivative. So this is going to be a vector field L sub x of y at P. So this is defined to be the following. So let me draw you a picture of the Lie derivative. So it's a sort of derivative of the vector field y along the integral curves of x. So what I do is I take a point P and I have, let's say this is an integral curve of x. If I don't finish the proof, we can join again. I'll just take a few minutes to finish the proof, okay? So, so what I do is I look at phi t of P. So over here, I look at the value of y here, okay? So that this gives me a tangent vector y at phi t of P. So this belongs to the tangent space here. Right? Now I have the tangent space at P and phi minus t maps phi t of P back to P. So the derivative d phi minus t will map this tangent vector back to some tangent vector here. And then here I also have the vector y at P. Then I take the difference of these two vectors. So this tends to 0 at t as t tends to 0. but the difference is first order in t. So what I do is I divide by t and I take the limit as t tends to 0. Okay, so it's a sort of derivative of the vector field y with respect to the vector field x. Okay, so so here's the definition. It's the limit t tends to 0 d phi minus t of y of phi tp minus yp divided by t, limit t tends to 0. Okay, note that this difference makes sense because both of these belong to the same tangent space, the tangent space at P. Is this clear?
Yes.
Yes, yes.
Okay, so the question is, does this limit exist, right? So what we're going to prove, so I don't think we might finish. So we'll join again and I'll finish the proof also. So this LXY, this limit exists and it equals nothing but the bracket of x and y. It equals the bracket of x and y. So this gives, the bracket was defined purely algebraically. This Lie derivative gives a geometric interpretation of the bracket. All right. It gives a geometric interpretation of the bracket. So let's prove this. The proof is not very long. So given a function f in C infinity m, you look at a function of two variables. One is a real number and one is a point in the manifold m. So look at h of t comma p, which is f of phi t of p, this function. All right. Then by the fundamental theorem of calculus applied to the t variable, I can write h of tp as h of 0p plus the integral from 0 to t dds, this should be a dds, dds of f of phi s of p ds, right? This is just fundamental theorem of calculus. Okay. Yes.
Yes, sir.
Okay, so now what is h of 0p? When t is 0, then this becomes just f of p, right? Because phi 0 is identity. So this becomes f of p plus the integral from, now I'd make a change of variables. I replace t by 1. Okay, so I make the change of variables. I divide by t basically. Okay, so I make this an integral from 0 to 1. So this becomes del h del t. And now I use, I look at this f of phi t of p. This is htp. So this becomes del h del t of ts comma p into t ds. Is this clear? I've just made a change of variables. I've made, my new variable is the old variable divided by t. All right.
Yes,
So
sir,
that
it is fine. Yeah.
the integral becomes from 0 to 1. Okay. Now I can write this as f of p plus I get a factor t coming out. This becomes t times some function g of tp, where g of tp is this integral from 0 to 1. Right? This is a function of t and p. S is a dummy variable here. Right? This is some smooth function here of t and p.
Yes, yes.
Okay, there's less than 1 minute. So instead of rushing, let's just wait and join again. It will just take me 2 minutes to finish the proof once we come back. Okay.